Okay, continuing on with what we have for acceleration, velocity, and distance. Okay, again, if we are looking at determining x in terms of t, okay, and we have given that the acceleration is equal to 3t minus 1, and we have at time 0, okay, we have that the velocity is equal to 4, and likewise at time 0, okay, we have for the case of the distance, initially we have to be equal to 2. And if we're looking at expressing x in parametric terms, okay, so again we have for acceleration, again that will be the change in velocity with respect to the change in time. Okay, so again we have dv over dt is equal to a, which is equal to 3t minus 1 as given. Upon looking at separating the variables, in this case the differentials, okay, so again we have the dependent variable or the velocity to be v, and the independent variable we have in reference to time, which we have at t. And looking at separating, okay, so we have that dv is equal to the quantity of 3t minus 1 dt. And looking at integrating, so we have for the antiderivative of dv, this goes directly to v. And for the quantity of 3t minus 1 dt, okay, we have the antiderivative terms at 3/2 of t squared minus t. And it is on the right-hand side of the equation that we can apply a constant. And we would just designate this once again as c sub 1. And we have now, again, at time 0, okay, we have that the velocity is equal to 4. And applying the condition supplied, okay, for the velocity given the time t is equal to 0. Okay, so plugging in 0 for t and 4 for v. And if you notice, okay, whenever t is 0, 3/2 of t squared becomes negligible. Likewise, negative t is also at 0. And so automatically we have for the value of the first constant, this will become equal to 4. And so we have in the rewrite, we have for the velocity in parametric terms, this will be equal to 3/2 of t squared minus t plus 4. And creating the pathway to solving for x in terms of time. Okay, so again we have by definition, we have that the velocity is going to be the change in distance with respect to change in time. Okay, and we have designated in parametric terms the velocity to be defined once again as 3/2 of t squared minus t plus 4. And once again, separating the variables, or in this case, the differentials. Okay, so you're going to have dx isolated, and this will be set equal to the quantity of 3/2 t squared minus t plus 4, followed by dt. And integrating over both sides. Once again, so antiderivative of dx becomes x, and we have x equal to, and we have with the power property. Okay, so the antiderivative of t squared will become 1/3 of t cubed, and taking 1/3 of 3/2, so this will be 1/2 of t cubed. And for minus t, antiderivative will become minus 1/2 of t squared. And we have plus 4t. And we have followed by the second constant. And solving for c sub 2. Again, creating the pathway, we have utilizing the condition laid out for the distance at time 0. Okay, so that is equal to 2. And for what we have in the setup, once again, we have with x naught. So once again, we have with x naught equal to 2, and substituting accordingly. Okay, so x is equal to 2, and for what I have in t at 0. So we have the first three terms will become negligible, and right away we will have that c sub 2 is equal to 2, and putting back, and we will have the solution for x, which in this case is going to be 1/2 of t cubed minus 1/2 of t squared plus 4t plus 2. And that will be the final result. Okay, now I'm going to give you a case of looking at a situation where you might not have the distance or the constants to be the same as what we have for the initial conditions for the velocity as well as the distance. Okay, and let me give you just a bit of a backdrop. And let's say that in terms of integrating, I'm going to stray a little bit from the velocity, acceleration, and the distance, but I'll get back to it. And let's say that if you're taking the integral of the square root of x plus 2 dx, and we have in terms of rewriting, so going from a radical to an exponent. Okay, so you have the quantity of x plus 2 raised to the 1/2 dx, and we have with the power property. Okay, so in this case, for this side we have x plus 2 for the variable expression inside the parentheses, and the derivative of x plus 2 just goes to 1, so I do not need to perform any kind of u substitution or the like. So I can just go with the power property. And for the antiderivative, okay, so we have for x plus 2, we add 1 degree to 1/2, so this will be to the 3/2. And the coefficient in front will be what results whenever you're dividing by the initial power added to 1. So dividing by 3/2 is going to be the reciprocal, where upon we're going to have 2/3 of the quantity of x plus 2 raised to the 3/2, followed by the constant. Now, let's say that if you're looking at x times the square root of x plus 2 dx, and one pathway is to utilize integration by parts. So for what I can do here, and as a reminder, going back to earlier calculus classes, okay, so for the integral of u dv, that is going to be equal to u times v minus the integral of v du. And some textbooks might have it as v times the integral of du. And looking at what we have here, if we go through the process of integration by parts, okay, you can set u equal to the expression that will lead to a simpler differential result once we take differential. Okay, so between x and the square root of x plus 2, we can get to the differential a bit more quickly with x. So we have u is equal to x, and taking the differential for that part, we have the du is equal to dx. And for what we have for the dv part, dv is equal to the square root of x plus 2 dx. And taking the antiderivative, and guess what? We had the integral of the square root of x plus 2 dx, and for the antiderivative term, okay, this will go to 2/3 of the quantity of x plus 2 raised to the 3 halves. And for what we have in the setup, okay, so you have u times v. So u is at x, v we have at 2/3 of the quantity of x plus 2 raised to the 3 halves. And so we're going to have multiplying the expressions together. So you have 2/3 of x times x plus 2 raised to the 3 halves. And here for the negative of the integral of v du, you can see we have minus, and just to make things a little simpler, I'll go ahead and take the 2/3 outside the integrand. So we have minus 2/3 of the integral of x plus 2 to the 3 halves dx. And for what we have in the follow-through, so we have the first antiderivative term. So just kind of repeating this. And what I will do here, okay, for x plus 2 to the 3 halves, the antiderivative, okay, we'll just go ahead and write this. So just like x plus 2 to the 1/2, once we wrote the antiderivative, we increased the power by 1. Well, for x plus 2 to the 3 halves, if I increase the power by 1, this will become x plus 2 to the 5 halves. And the antiderivative of this integral, okay, you'll be looking at x plus 2 to the 5 halves divided by 5 halves, or multiplying by 2/5. And clustering this with multiplication by negative 2/3 is going to turn out that in the complete follow-through, we have 2/3 of x times the quantity of x plus 2 to the 3 halves minus 2/3 times 2/5, which will be negative 4/15 of the quantity of x plus 2 to the 3 halves followed by the constant. Now, integration by parts is a viable option, but in the realm of working with acceleration, velocity, and distance, okay, for these types of problems that might incur such integrals, there is another route. Instead of integration by parts, we can utilize u substitution. And what I can do here, say that if I let, in this case, if I have u equal to x plus 2, and taking the differentials, I have du is equal to dx. Okay, now, if you notice, I have a couple of x terms here. I have the square root of x plus 2, and I have x, the variable coefficient at the front. And if I were to write x in terms of u, I'm going to have that x is equal to u minus 2. And so working with this same integral, but putting it in the realm of u substitution as opposed to integration by parts. So we have in lieu of x, okay, we have the quantity of u minus 2. And for the square root of x plus 2, so I have the square root of u. And for dx, okay, dx goes to du. And for what we will have in following through, okay, so we have u times the square root of u. So think of this like as u to the first times the square root of u, which would be u times u to the 1/2. So we'll be looking at u to the 3 halves. And we have minus 2 times u to the 1/2. Quantity du. And for the antiderivatives, and still working with u substitution. All right, so I have 2/5 of u to the 5/2. And we're going to have u to the 1/2 antiderivative is going to be 2/3 of u to the 3/2 and multiplying by -2. So this will be minus 4/3 of u to the 3/2 followed by the constant. And for what we have in back substitution, so this will become 2/5 of the quantity, okay, of x plus 2 to the 5/2 minus 4/3 of the quantity of x plus 2 to the 3/2 followed by the constant.